Good morning, everybody. Thank you for joining us today at another webinar series for Lighting Design Lab. My name is Armando Berdiel, and today I'm going to be joined by Dwayne Donlin with the Seattle Department of Construction Inspections, as well as Jason Acosta and Denali Jones from RDH Building Sciences. Today, we are going to be discussing a topic that we are bringing back from the beginning of this year, 2018 Seattle and Washington Energy Code. And today we're talking about the building envelope side of this code. So now, if you're familiar with this, before we begin, you'll notice that everybody is muted, but please continue to engage with us by using the chat feature at the bottom right of your GoToWebinar dashboard. We will be stopping periodically to address questions or comments if you want to engage with us in the chat again, and we'll have our panelists address your questions as such. Following the webinar is going to be about a 30-second survey of how we did, how was your experience, please fill it out. And also wanted to let you know that a recording of today's webinar, as well as a copy of the slide deck, is going to be available on Lighting Design Lab's webpage. Any last or additional questions or comments, you can email us at lightingdesignlab@seattle.gov. Next slide, please.
And note that this is now being recorded. Is that correct?
That is correct. And just wanted to be very quick here. Today's webinar delivery hosted with Lighting Design Lab, partnered with the Seattle Department of Construction and Inspections, RDH industry partners that are going to be experts, subject matter experts here, and all powered by Seattle City Light. I think that is it for me, Dwayne. Without further ado, you guys can take it away.
Okay, we've got a lot of stuff to go zooming through in the next 2 hours. We'll give you a break in the middle somewhere, and thanks for everybody jumping on here. We'll just start with it. As you know, we got all kinds of codes that apply to buildings, and energy code is just one of them. And yet it's one that's attracting a lot of attention because it changes frequently and it's pretty complex. There's a national standard, the IECC, that is turned out every 3 years, and that's was known as the 2018 one. So in 2019, Washington State's, and it's you're adding amendments to the 2018 IECC, and then we spent last year adding amendments for Seattle, and those have all gone into effect now, with the exception that the heat pump water heating is only going into effect in January 1st, and that's the date that permits are applied for. So more background: we've got state and city goals that we're required to meet, and these are in legislation. I think people with expensive suits come up with these things sometimes and then toss them over their shoulders to people like us and say, okay, make this happen. And so we are, in fact, making this happen. And that one on the left, the 70% energy reduction, that's between, like, it was 2008 they passed that law, and 2030. So we have this 22-year period. We are more or less on track at the state level, and now they've added specific targets for reduction in greenhouse gas emissions, and Seattle is saying, yeah, and by 2050 or sooner, depending on some other pending legislation, Seattle's supposed to be running completely carbon neutral. So we had these 4 guiding principles for how Seattle amendments were put together, and we'll be focused today on the envelope part, of course, and that bottom line there is the bottom line, that the buildings we're building today have to be capable of getting to that 2050 carbon neutral standard without having to rip them apart and rebuild stuff. So envelopes, which are going to last 50, 80 years before they're substantially altered, they need to be done right now. So this is the envelope is not nearly as exciting as other fun things like, you know, LED lighting and solar panels and stuff, but it's really critical because those energy savings you come up with the building envelope are very, once they're put in correctly, they're very long lasting and continue to save energy for generations. But no, once they're done, nobody sees it and nobody can appreciate what a great job you did. You know, chapter 2 is the definitions, which is pretty dull, but chapter 3 in the code is even duller. It's got you know, these sort of background rules for how you put in insulation, and there's some default values for various kinds of fenestrations, which you should not ever use unless you absolutely don't have any way to determine what those are, because they're extremely conservative. Got some spandrel panel values in there. If, once again, if you've got real values from your manufacturer, it's better to go there. Because since we had to pick like the most, for those default values, we had to pick the most conservative states, almost everything will be better than that. And speaking of chapter 2, it's there are a lot of definitions in there that are not just really obvious to people who haven't read them. So since you're all an exciting bunch of people, I'd suggest you go and look through those definitions in chapter 2. Anytime you see it italicized in the text, you can know that it's defined back there. So next, and don't worry, it won't be me all morning. We'll be getting together with Jason and Denali in a little bit. A mass transfer deck is not like most things you might think. It is where, like at the podium of a building, where it transitions to a tower, and you have there's a deck that comes all the way out to the property lines to enclose the parking. That would be a mass transfer slab where you're actually transferring load from a column line or a wall line out to another column line. And so that's a special spot, and we've given it some a little bit of leeway for calculating what the heat loss is through there, because we know you just can't. There's no way to actually insulate that transition. We specified in the Seattle code here that cantilever decks are not mass transfer slabs. Those are not transferring load from above to below. They're just poking out into the air. And you'll hear a lot more about options for exterior decks in a little bit. We made some changes where there's a slab that's going that's cantilevering out there. We're saying, well, you can either use R10 insulation with one of those insulated deck support assemblies, or you can, if you're gonna work with it with a UA calculation, it's going to be a 0.1. And that's a lot easier to achieve than the 0.052 or something for other building types. And then you see down there at the bottom, just for clarification, at the request of many designers, we've made it clear that when you're poking down through the say into the garage from a building above, an unconditioned garage, that column or structural wall that's coming down does not have to have the same U value that your insulated slab assembly would have, because obviously it's not going to happen. And finally, where you've got a utility vault, your electrical is coming in there, that slab right above it that's connecting to the building does not have to be insulated, because the City Light just doesn't let you put insulation inside of their vault, and it's really hard to put it outside, and it's probably pretty warm anyway. So I think that we're on to RDH here, and Jason, you want to say hello and introduce yourself a bit, Jason?
Sure. Hi, I'm Jason. I've worked with RDH for 7 years. I'm an enclosure consultant. That's what we do at RDH Building Science. And I also do energy analysis. That's my training. And I do a lot of energy code compliance submittals. So I don't think the thermal envelope is boring. It's what I do for a living. So hopefully I can impart some of my enthusiasm through this presentation and keep it from being too dry. I will say that change for the electrical vaults, that the transformer vaults that Dwayne just discussed, was a welcome reprieve. That's always been super challenging to figure out how to make up for those uninsulated floors, because we just can't insulate them. So while the code's getting harder, there are a few changes that are to make it practical as well. Okay, so we're gonna jump into the changes in the code, starting with wood framed walls. So here I've got the R value tables from the energy code presented right here. And the 2015 code, both the WSEC and the SEC, required R21 insulation in a 2x6 wall with a 16-inch on center framing, intermediate framing as defined by the code. The code is changing now. So in Washington State, we've got the Washington State Code, we've got more stringent requirements for Group R occupancy. So that's residential occupancies. Now, we're talking about the commercial code, but residential occupancies within the commercial code. So buildings that are 4 stories and higher, essentially. And in Seattle, all occupancies have these tougher requirements. So what's required? There's a few options listed in the R value tables that don't take too much explanation. You've got a 2x4 wall, you put an R13 bat, R7.5 continuous exterior insulation, or a 2x6 wall with about R4 exterior insulation, or R25 insulation, which if you're doing bad insulation or blown cellulose or blown fiberglass to fit R25 into a wall, you need to increase the stub depth. So you're talking about a 2x8 wall for conventionally insulated walls. Next slide, please, Dwayne.
Yeah, and let me just interrupt. And anybody who's not familiar with it, WSEC is Washington State Energy Code, and SEC is Seattle Energy Code. And do look over on the table at the left at the bottom. You can see that up until this year, we always said a 2x6 wall with bad insulation in the empty studs spaces was good enough. And that's not true anymore.
Not true anymore. So I'm going to go into some more explanation of what we need to do to meet these new code requirements. So those are the R value tables. They lay out a simple way to meet the code. When that's not possible, or we want to look at alternates, we do U-factor calculations based on how it's outlining the ASHRAE Handbook of Fundamentals. So we did a few of those calculations to just examine some different scenarios and present those to you all. So one option worth considering is rather than 16 inches on center framing, increasing the stud spacing to 24 on center. In the past, I've met a lot of resistance to this. Wood frame buildings have always been framed at 16 on center. So the resistance is primarily from the contractors. So if you want to examine this, they're the first folks to talk to see if they feel it's realistic. Now, if you can get them on board, there's some potential cost savings here. We're using less wood. Next, talk to your structural engineer. They're going to have to design it for that as well. One other thing to consider with 24-inch on center framing is there's been a lot of cladding systems that have been developed for attachment at 16 on center. So if you've got like a gypsum sheathing, a non-nailable sheathing where you need to contact those studs for your structural attachments to your cladding, you may be limited somewhat in your cladding options. With many that's not the case, but it's just something another wrinkle to consider. But yeah, in the past we've met a lot of resistance at RDH to 24-inch on center framing. I think it's going to be revisited now because these other options are adding some cost. So one to keep thinking about in consideration. So the next option, as I just discussed, was 2x8 framing at 16 on center with an R25 bat. So you can get bats that fit into that size framing that achieve that R value. As far as we know, there are no bad insulations, whether it's mineral wool, fiberglass, blown cellulose, blown fiberglass, that meet this requirement to get to R25 in a 2x6 wall, as far as I'm aware. So the third option here is with 1 inch of continuous mineral wool insulation. Dwayne, could you give me a click, please? I presented an image here, an illustration. There it is, to show one way of going about this that we like at RDH. So what this image is showing is it's showing a wood stud wall. Now in this image, the stud cavity is not insulated, but as we've discussed here on the screen, it's you got to insulate that stud cavity between your interior chip and your exterior sheathing with R21 insulation. And then we've got a continuous layer of mineral wool insulation, and we have furring strips that are attached directly to the studs through the mineral wool insulation. So you've got to line up the furring strips with the studs, select the appropriate size screws, and a direct attachment. It's cost effective. It works. We've done it in the past quite a bit. There's occasionally some convincing, some contractor training that needs to go on. Occasionally they miss a stud, so you want to check before you put your insulation in that stud cavity to make sure they've hit the studs rather than missing. But it's effective. We'd actually give a whole presentation on this, and the structural testing's been done. It's appropriate for fire resistance as well. So it's one method that we like. There's also the other cladding attachment methods, thermal clips, etc., that can be used. But this is just one way that to kind of avoid that's cost effective. So that's one method to consider now. And then the final is the flash and bat. And if you please click again, Dwayne. So a flash and bat is what it's colloquially referred to as we put a couple inches of closed cell spray foam in the stud cavity, and then fill the remainder of the cavity, the remainder 3.5 inches, with a R15 bat, approximately. And this works. This meets the U factor requirement of 0.051, that updated requirement. However, it's worth kind of just considering this from a risk point of view. So closed cell spray foam, it's got a high RE value per inch. That's why we're putting it in the wall. It's also an effective air barrier, but it's a vapor barrier. So it's going to eliminate essentially drying potential from the exterior to the interior. So Seattle, we've got a very damp, wet climate. There's really no drying potential to the exterior for 6 months straight. Fall, winter, early spring, we don't dry to the exterior much. It's a tough climate on wood frame buildings. So if you're going to take this method, you're taking on some additional risk. We recommend definitely a rain screen cladding attachment. You want an air gap between your weather barrier and the backside of your cladding. Maybe upgrade your weather barrier to a self-adhered vapor permeable sheet or fluid applied weather barrier. So proceed with caution. It's usually not our first choice from a risk point of view, but if it's done right and properly, it can be effective. It's just one of those things that definitely you're adding some risk. So yeah, be careful about it. Okay, next slide, please, Dwayne.
All right, and now we're on to air barrier testing, which went through a pretty big shift this year. Not only did the standard lower from 0.4 CFM of leakage per square foot of your envelope down to 0.25, but up until now, we always said you have to pass, you have to do the test, you have to report the results, you don't have to pass. But that is in the past now. You do have to pass, and you don't have to hit the 0.25. The 0.25 is what you're shooting for. If you're worse than that, but still better than 0.4, then you just have to do the same routine we did before, which is go around the building, find the leaks that you can find, using a smoke pencil or something. Fix all the leaks that you can and write up a report. But you can't get a certificate of occupancy anymore if your leakage is worse than 0.4. So making a plug not just for RDH here, but basically for all the legitimate building science firms around. I don't think we've ever seen a building fail that hired and paid attention to a professional envelope consultant that has building scientists on staff. But some of the others, they might have problems. But with that, I think that Denali is going to have a few things to say about this issue, right?
Yeah, thanks, Dwayne. Yeah, I'm Denali Jones. I also work at RDH Building Science. I manage a lot of our air barrier testing that we do here in Seattle and also just across North America. And I'm going to be condensing what should be an hour presentation into about 5 minutes. So bear with me. I'm going to generalize a lot and oversimplify some things, but hopefully I'll have a few useful nuggets in here. So I'm going to be talking about the 3 keys to airtight buildings, really the 3 phases, and each one of these is really important. And where we've seen problems is where one or more of these fall down. And I also, I just want to emphasize that, none of this should really be new or groundbreaking. We've had air barrier requirements for over 10 years now in Washington. So we've been supposedly doing this on every building for a long time now. And so some people have gotten quite good at it. Others, I think, still might need some help, and that's why we're here. So next slide. Dwayne? Yeah, there we go. So yeah, it all starts with the design. Hopefully there's some architects on the call. I don't want to beat up on you too much, but this is where we see quite a few problems crop up in design issues that are not fully resolved until it's well into construction. So the first step is to define and identify all your assemblies, your enclosure assemblies, and define where the air barrier actually needs to be in the building. So like, is the mechanical room on the roof part of it or not? Is the storage room in the parking garage, is that part of the enclosure or not? Just defining where you actually need to have an air barrier and where you don't is really the first step. And then once you have that defined, then you need to go to the next level, and within each assembly, there should be a part of that assembly that is the air barrier, and it really should be called out as that, like with a call out on the drawings, this is the air barrier. It may also serve another function like a vapor barrier or closed cell spray foam, which is also a thermal insulation, but it should be defined as, this is what we intend to be airtight. And then from there, you can start to identify all the key interfaces. So where all the assemblies intersect, where the wall meets the soffit or the roof, how does it transition through the parapet? What are your window details, all your penetrations, your louvers? The simplest way to work through these is once you start detailing, you should be able to draw a continuous line through every single detail, every section cut, every plan, where the air barrier is located. And if you have to pick up your pencil at all, then you fail. That's really as simple as it can be boiled down to. So the key word here is continuity. It has to be continuous through every single one of these details. So that's relatively simple to do in 2 dimensions, but the problem is buildings exist not just on paper, they exist in 3 dimensions. And that's quite often where we see things fall flat is, people not thinking kind of into and out of the page, what happens beyond. So, once we get into construction, we try to identify these conditions before they become a problem and work through how we're going to do it. And that transitions me to the next phase, which is actually building an airtight building. And I'm not going to sit here and tell you that construction is easy or simple, but I do want to hit on some of the keys that we've found that make at least the air barrier part of construction a lot simpler and will set you up for success. And the first one is just pre-installation meetings. And I know that's not cool or exciting, but it really is. It's so important just to get everyone in the same room, or at least on a Zoom call together, and talk through the enclosure. This is your your last chance to go through shop drawings and submittals, talk about who's going to be doing what and when they're doing it. And by everyone, I mean the architect, the contractor, their subcontractors, the manufacturer's reps, enclosure consultants, and also the owner. If you need to make any kind of decisions about changing anything, just having the owner present is really important. So, you know, this is just your last chance to find out who by others will be. So nothing gets missed. This is quite often where things fall flat, is where there's just some missing scope. No one picked it up. Who knows who's sealing to what membrane, and the order matters. This is where you need to not just think in 3D, but also add that fourth dimension of time. This photo just shows a classic example of, you know, where the siders went first. They put up their air and weather barrier membrane on the wall, and the roofers weren't done yet. So the roofers just came through and torched the crap out of it. Fortunately, you know, we caught it, and they replaced all this product and got a good air barrier tie in here. But it's the sequencing matters a lot. And then the next key here is the mock-up phase, where, you know, it could be as simple as just going out and watching the first window installation in the building and seeing how they're going to seal the window to the wall. Or it could be building a full freestanding mock-up with, you know, like a 6-sided box, doing roofing transitions as well, or anything in between. But it's such an important part of the process to, you know, to just review the first in place work, or build a separate freestanding mock-up, just to make sure that, you know, everyone's there, everyone agrees, okay, yes, this is how we're going to do this going forward on the rest of the building. And just having that smooth process from the mock-up into the rest of construction is critical. And then the final thing in terms of the, you know, building the airtight building is we found that more often than not, there are quite a few GCs around town that actually have their own full-time quality control person or people, in some cases, that review the envelope. They essentially do what RDH does, but they do that full time. They're there every single day. You know, third-party consultants like RDH, you know, we're generally not there every single day on site. You know, no one wants to pay us that much, but just having someone who's dedicated to that role on the GC side, really hold people accountable on a daily basis, is really a great way to do it. And the GCs that we work with that do this, they tend to have a lot tighter air test numbers than the ones who don't. Next slide. So that kind of just leads right into the confirmation process, and this is really just quality control. So this is some people think of this just as the whole building air leakage test at the end of the project, but that's really, I like to think of that as like the final exam. You really have to do all the homework and study beforehand. So that would be doing, you know, visual review. You have to do some, quite often, just qualitative testing. That could just be anything from going up and, you know, pulling on a self-adhered membrane. Is it really actually stuck? Are they using primer? Did they roll out the laps? Or quantitative testing, you could actually do a peel test and get an adhesion number in pounds per square inch. Or you could do you know, a sealant pull test to make sure the sealants are actually adhering well enough. All these things just kind of go into the overall quality control of the envelope and the air barrier specifically. But you have to go confirm that it's being done properly. You can't just assume that because you've done all the mock-ups and the pre-installation meetings and you've got a good design that you're going to catch everything, or that you've already caught everything in those phases. You have to go look at it through construction, because there's inevitably going to be some details like this picture here where no one really thought through this soffit transition. You know, you can't, there's no building that I've ever worked on where they drew every single detail on the entire building. No one drew a detail through this soffit, and no one really thought about how the air barrier would transition to this underside of this metal deck here. So fortunately, we did see it, and we worked out a detail, and they were able to get that sealed up, and this building ended up being quite airtight. But you have to go look at it. You have to confirm that what's being done is actually going to work.
Denali, we have a question in chat as people are inspecting the building. Do they use IR cameras as people are walking around the building?
Yeah, absolutely. So that would fall under the the qualitative testing. We do that quite a bit, where you can. It's quite easy. It's a lot easier if you actually can pressurize or partially pressurize a portion of the building. And then you can look with the IR camera and you'll see air leaking out. It's going to change the surface temperature of where it's leaking around. So we've done that before, where we've done mock-up tests on like a single unit or even a whole floor of a building that got closed in, and you can pressurize it and look for air leakage with an infrared camera. You can also use smoke, like a theatrical fog machine, to trace leakage paths. That's a great way to do it. But yeah, it's important to do all this stuff during construction while it's still possible to fix it, because like I said, the whole building test at the end, you can think of like the final exam. And so if you've done all your studying, you've done all the homework, passing the final exam shouldn't be that hard. But if you try to cram last minute, it's really not going to work well. It's quite often too late to make wholesale repairs to the air barrier during the whole building test. It's already generally covered up at that point. So it's going to take a substantial amount of work to get back to that air barrier layer and perform repairs.
All right.
Yeah, back to you, Dwayne. I'm happy to answer more questions as they come up.
Yeah, I think we'll definitely have some. Here's just diving back into the code itself. Another thing that at the state level for this code, we said that you could be a semi-heated building even if you were heated with heat pumps, but with the cooling capacity permanently disabled. But there were some problems with that. Like, it seems like permanently disabled means something that could actually be re-enabled with a factory tech and a screwdriver in about 10 minutes. So and it just didn't seem to be in the spirit of this. So we're making it clear that if you want a semi-heated building, and the only advantage there for you is that you don't have to put in the insulation in the opaque part of the walls. All the other insulation has to be in there anyway. But just having heat pumps doesn't qualify for you. We also in this section said that it was okay to get some infrared heating for some specific applications. We've seen repair garages where they keep the garage door open in the winter, and this would just be an infrared heater over where the mechanics are working, so they can not be freezing their fingers there. We've seen there's a desk in warehouses sometimes where things are being checked in and checked out of the warehouse, and so you could have one there. So we're giving you a little bit of a break. Glazing percentage, through a kind of last minute negotiation, we ended up with the prescriptive path allowing 35% wall area to be glazed in instead of 30, which is in the main code. And really, the only buildings that I've seen that need more than 30% glazed area are high-rise office and high-rise residential. Everything else I've ever done, schools, hospitals, retail low-rise residential, they all just do fine with 30% or less. But there's a couple of exceptions there. If half of the floor area is in a daylight zone, which is very hard to do unless you have extremely skinny floor plates, you can bump up to 40% glazing, and you can also bump up if you have very low U value glazing systems. With the modeling path, this is new now, since we're using the Appendix G method from ASHRAE 90.1 for modeling, and that instead of just having this across the board limit to the amount of glazing, sets a different percentage for each different building type. I think there's over a dozen types that are listed there, and each of those is allowed to have not only that amount of glazing, but if you have less than that amount of glazing in one of those types, then you're allowed to take some modeling credit for it. There are a number of building types that are not listed in that list, most importantly, multifamily. And so with that, they use the old method, which is that it's either 40% that you use for your baseline model, or if you're using less glazing than that in your multifamily building, then you just enter that if it's 32% or whatever. So it's a little bit of a mixture now. So we did reduce we changed the framing, the method of describing fenestration. It used to say, metal and non-metal, and now basically the top one, 0.38 U value is for all kinds of site-built fenestration, plus what's called Class AW windows. Don't use it much here around Seattle, but if you have a very tall building that has big wind exposure, or maybe you're right next to a large body of water, you might have to go to Class AW. But otherwise, pretty much all punched window openings would be in that all other category, and that has a more stringent U value of 0.3. In Seattle, we're going a step more stringent than that, and so it's 0.34 versus 3.8 for site-built stuff, and then 0.26 instead of 0.30 for the all other, with a little bit more U value allowed for operable windows. These are all available in very high-end double glazing, so triple is not necessary. Jason.
Okey-doke. I'm gonna go to the next slide. Oh, there it is. I'm just going to talk a little bit more detail about the change in window classifications, and also just list some real-world examples of what it takes to achieve these lower U value requirements in the city. First of all, so we have this new category. Rather than metal framed, it's Class AW site-built and curtain wall, like Dwayne mentioned. So what do we mean? So like anything else in Energy Code, if you're not so sure, first place to go is Chapter 2, the definitions. So site-built fenestration, definitions on the screen right there. Field assembled units, factory formed or field cut glazing, or field cut windows. Am I reading that right? Field assembly units using specific factory cut or otherwise factory formed framing. Read from the definition there. Such as storefront, curtain wall, window wall falls into this category too. So that's what site built is. And then Class AW, what do we mean by that? So this is it's from the North American Fenestration Standard, NAFS. It's their standard specification for window systems. So Class AW is the most severe duty window. It's intended for mid-rise, more often high-rise construction. And that's typically what we specify on those buildings, but not often on even mid-rise multifamily or low-rise construction. So what does it take to be Class AW? There's performance requirements. I've listed a few on the screen in the bottom table there. There are minimum design pressures and structural test pressures, so 40 PSF, so that's kind of like a wind pressure. And then it's tested to 60 PSF, 50% higher than that per NAFS 101, which is a standard specification for these window systems. There's a minimum water penetration resistance of 8 PSF. These are some of the key kind of baseline gateway requirements to meet Class AW. There are other requirements, especially for operable glazing. I'm not going to get into, that's the whole subject matter on its own. But yeah, most often this is curtain wall, window wall. It's very rare that a punched opening like a vinyl window is going to meet these requirements. So they go hand in hand with the site build in the Class AW. So we've got lower U value requirements in the city of Seattle. I kind of want to talk about what it's going to take to meet these requirements. So we've gone from 0.38 in the state code to 0.34 in Seattle, the U factor requirement. What do we need to do to get there? And I think the city's intent, and I think they got the U value just about right, is to weed out the worst performers. So a classic example for storefront windows, to take a super common storefront system, is the Conair 451 storefront system. So they've got a 451T, a thermal system, and a UT, an ultra thermal system. The difference between these two primarily is that the UT system has 2 thermal breaks, whereas the T system has 1. So only the UT system is going to meet this requirement. For standard double pane glazing, you know, all of our glazing now has low E coatings, inert gas fill, warm edge spacers. We're kind of just moving that way in the code generally. Anything that doesn't have that is more or less not going to meet these requirements. I gave an example from one manufacturer. Other storefront manufacturers, EFCO, they've got similar systems with two thermal breaks that are going to get there for storefront requirements. Most stick-built curtain wall, you know, thermal stick-built curtain wall is going to be able to get to 0.34 as well. It's not too difficult. There are some unitized systems, some of the older ones that are having trouble with this. Some manufacturers are taking a closer look to improve their thermal performance because, you know, they need to now. So again, weeding out the worst performers, but there's a lot to choose from. Window wall too. The most conventional window wall, you can just about get there. The operable windows and window wall, they tend to be a bit less performing, so you gotta take a close look at those. But yeah, we're weeding out the worst performers, and you know, the thing is now is that the windows aren't significantly outperforming code. So that's something that we're going to get into later that may cause us some issues as we're doing our code compliance calcs. Our windows are just, they're barely going to be getting by. So next slide, please.
Hey, Jason, if you don't mind, if we have a moment for one quick question here. Awesome, and it reads, do concrete columns and walls that penetrate a thermal envelope floor have to be insulated per the 2018 SEC table C402.1.4? How is this U0.55 achieved for concrete columns and walls that penetrate a thermal envelope floor?
I think the intent there is about the U value of the concrete that's penetrating an insulation layer for that floor. So if you do the math, you're going to get to about U.55. So whereas before we would get corrections response from the city, hey, you forgot your columns in your calculations. Now if you do a calculation that basically takes into account the thermal resistance of the concrete through the thickness of the insulation layer, you're going to get to about that U factor, so that it's no longer a negative in the component performance calculations.
Well,
anything to add there?
Yeah, it's a big negative actually. A really tiny bit of concrete, uninsulated concrete that's exposed all the way to the outside, because, you know, we architects want to be honest in our expression and blah blah. It's very hard to make up for with more insulation elsewhere in the building, and there are these other problems. The fact that you've got now a cold spot inside your building that's going to start attracting condensation and so forth. So I think exposed concrete that has gone all the way through the insulating layer for a column and is not any, it means that somebody has failed an IQ test.
Yeah, okay. Exposed concrete is a huge thermal bridge. I think I guess how I saw the question was an interpretation of how that the change in the Seattle code that gives an allowance for those for concrete columns that are, for instance, through a park an insulated garage ceiling into
Right. I thought we were talking about the outside. Yes, if they're just penetrating the floor and going down, then yes, we're allowing you to do a reasonable sort of calculation and not holding you to that what is it, 0.32 or something like that that is normally required for floor slabs. Right.
Yeah, I don't disagree with anything you said. There's just an extra allowance in the code now for those floor penetrations, those penetrations through insulating floors for structural elements like columns. Okay, well, now we're going to take a quick look at the requirements for which is 0.26 for punched windows, the other window category in Seattle. Again, like, you know, your standard vinyl windows, your good performing ones like BPI vinyl windows of the world, they can meet this 0.26 requirement for fixed, 0.28 for operable without any, you know, major modifications. We just got our standard, you know, double pane window with a low E coating and inert gas fill. Some of the lowest performing ones might not quite get there, but it's really not too challenging. The issue is that, like, you know, a lot of these windows will get right to 0.26, maybe 0.25. They're not exceeding this a lot. And so when you're doing your component performance calculations, if you're doing a UA calculation to show compliance with the code, you're taking that path to prescriptive compliance. Historically, what we've done, I've been doing this, a ton of these calculations, I do them all the time. What we've done in the past is we've had overperforming windows that were better than the code, and we've traded those off to make up for our thermal bridges, you know, uninsulated balconies, that sort of thing. Some of the stuff we're going to get into here soon. That math doesn't really work as well anymore. So we're really going to have to take a much closer look at our thermal bridges, and it's going to be a lot tougher to make up for them with overperforming windows. So I'll talk about that a little bit more later, but just something I wanted to add in there. Let's go to the next one, please, Dwayne.
Okay. Remember that if you want more glazing area, you can if you want to go to the 0.4 as your baseline, that's fine as long as you do this. And so you're going to go to in Seattle a U value of 0.3 to meet this for the Class AW and for all the site built types of fenestration, and a 0.22 for in Seattle for the all other, the punched window openings, and so that's getting to the very high end, right?
Yeah, I'll talk a little bit about what it's going to take to get there. So, you know, just to reiterate something that Dwayne said earlier, in previous codes, once you exceeded 30%, you had to take an extra step to increase your glazing ratio for prescriptive compliance. There's a daylighting option, but most often it's this high performance fenestration. Now, it's if you exceed 35%, you have to go to this step to get your glazing allowance up to 40% window to wall ratio. So what's it going to take to get to these lower U values that are required in Seattle's code? You know, it's for the Class AW, the high performance systems, it's getting more challenging for sure for all of them. But you know, so most off-the-shelf systems are not getting to U 0.30 without some modification. So of course, triple pane is a great way to get there, more energy efficient. But you know, there's extra costs associated with triple pane, and a lot of folks try to avoid it. So we've taken a look here at some options for getting there, and these are some things that we've implemented in the past as well. So one thing that we're hearing a lot more inquiries about is the addition of a surface for coating. So that's a coating on a double pane window on the interior surface, the surface that you touch from the inside. So it's a hard low E coating that reflects interior heat back inside rather than allowing it to transmit through the window. So these are effective, they save energy, and they reduce the U value of window systems. So I've got an example here where we had a stick-built curtain wall that had a U value of 0.32. We added one of these coatings, it changed it to 0.27. So that's the kind of difference that we're talking about here, meaningful. So physically, what happens is when that heat is reflected back inside, that interior window surface gets colder. So there's been a lot of hand waving and, well, we're increasing condensation risk, in which we are. We're making that interior surface colder, but some people dismiss it out of hand for that reason. And we think that's a little bit too big of a brush to paint for this. Seattle's got a moderate climate, and often, with these window systems, the glass is what we're not concerned about the surface temperature of the glass necessarily. It's like the glass to frame interface. If we're doing a thermal simulation to assess condensation risk. And so this alone, we don't feel like is a deal killer. Like, definitely examine it, do a condensation analysis, do your 2D thermal analysis, and see if you're concerned about condensation given your project specific conditions. If you're humidifying the interior, definitely take a closer look, but don't dismiss it out of hand just because you're making a surface colder. Another thing here is this is it's not a very new technology, but it is kind of new for a lot of us. It's been around for 15 years plus. The first generation of these coatings were bad. They were terrible. They were difficult to clean, easy to scratch. Definitely could not recommend them. We had a video we passed around at RDH of just a coating that we could easily scratch, but you couldn't really clean at all. And so we were like, this is like 10 years ago, like telling stay away, even 5 years ago. Now we're like on the second, third generation coatings from reputable manufacturers, Guarding, Pilkington, Vitro. They've all got these coatings. They stand behind them. They typically don't have special maintenance requirements. And most manufacturers will say, whatever you're going to do, if you want to scratch a coating, people worry about the durability of these coatings, you would have to, scratch them just as the effort it takes to scratch a coating, you'd actually scratch the glass itself. So they're no less durable than the glazing they're applied to. But even having said that, like, it's new, let the owners know, order a sample, kick the tires on it, scratch it with a penny, see how you feel about it, read the maintenance instructions, and give everyone a fair warning. But we feel that it's a technology, it saves energy, and it's worth revisiting, especially for code compliance, for the reasons we're discussing here. A couple other examples. This photo on the right is a fiberglass window wall. It's new to the market from Cascadia Windows. So we've got a fiberglass system that's site built that has impressive performance, a U value of 0.24. So if moving from a metal frame to a fiberglass frame system, there are real energy savings there. So because of the nature of these products, just what they're made out of, they're more energy efficient. So there's an option worth taking a closer look at. And we're seeing some of the Canadian window wall manufacturers that are popular locally. They're stepping up. They're coming to market with newer systems that are thermally enhanced, sort of like the 451 UT system, and they perform better. So they're right there at that 0.30. Starline Quest. They're popular manufacturers that installed a lot of window wall locally. They've got these systems, and if you're careful with your glazing selection, you've got the right thermal spacer, the right low E coating, you can get there. So there are options that don't involve triple pane, going to triple pane. But triple pane is great, from an energy and typically an acoustic point of view. Let's go to the next slide, Johnny.
And by the way, we're drifting a little behind schedule here.
Okay, I'll speed it up. I tend to ramble. Okay, so here we go.
Yeah, Jason, and I know that we're strapping for time, but wanted to see if we can get a question in as you were talking about product and technology available. What about radiant cooling on perimeter occupants, maybe for comfort?
That's
radiant
a big
cooling.
subject. I don't want to just blow past it. Radiant cooling is a method of cooling that it's kind of beyond the scope of this presentation. I think safe to say it can be energy efficient and effective if your loads are low enough, and a lot of the code is moving us towards that. But it really is kind of a whole separate can of worms that
Understood.
come up quickly.
All right, we'll put a pin on that, and then we'll save the topic for the future. Thank you.
Reach out to me afterwards. my contact info. We could talk. Triple pane window. So now we're on to the all other category. The U value is now 0.22 for 6, 0.24 for operable. Similar conversation. We can include a surface 4 coating on double pane windows. Got some examples of going from about a U value of 0.26 to 0.22, 0.21. with the addition of these coatings, that's one way to get to this high performance category without going to triple panes. Or just go 3 panes and go extra energy efficient. 0.16. You can even do better than that with some of the higher performance, heavier vinyl window systems. Just a word on 3-pane windows is that now we're getting a lot more questions about them. They're all not created equal. Some manufacturers create specific frames for 3-pane windows with a larger glazing pocket that are kind of just re-engineered for 3-pane windows. Other manufacturers shove 3 panes into the glazing pocket of their standard vinyl window systems. And they can do that. They're testing their windows, but where it shows up is, well, first of all, we sometimes get concerned about the larger windows, like are they structurally suitable for those? So take a close look at that. Make sure they're tested for your project's conditions. You've got test results, but also with the acoustics. When you're cramming these 3 panes into a smaller glazing pocket, what you often see is that the acoustic ratings don't improve, which they typically do for 3 panes, or they may even get a little worse. So some of the manufacturers take steps to do that, but one of the advantages of 3 panes is improved acoustics. So they're not all created equal, I guess I just wanted to say. Yeah, I think we can keep on moving, Dwayne. So there's been a lot of concern about costs for these, higher end glazing. So we've got some just cost anecdotes. We got we spoke to some manufacturers. We got some project experience for projects that we worked on. So what are we talking about? The cost increases. So we're working on a high-rise apartment building. We're replacing all these large sliding glass doors, and the increased cost from going from a 2-pane to 3-pane sliding glass door was about 35% installed. One anecdote there, so third higher cost for the switch to 3-pane. These thermally enhanced window wall systems, we've got a project that priced that, high-rise apartment building, about a 10% cost increase installed, 10 to 15%, $10 per square foot, 10 to 15% cost increase for those thermally enhanced window wall systems. About $7 a square foot, $6-7 for those interior surface low E coatings. So that's per square foot of glazing. So that's a cost increase. It adds up. It's 40-50% of the cost. And then this chart on the right, we got some input from the manufacturer and Sharon Libby at Walsh. I actually tweaked these numbers up a little bit since the last time we gave this presentation with some more information. But what we're showing here is that the cost to go from double pane to triple pane, about a 45% increase in cost. That's our baseline of these small or medium vinyl windows. And then there's a cost increase just for increasing the size of those. If you want this extra big vinyl windows that we see on a lot of multifamily buildings around town, just the increase in cost just for increasing the size, 35 to 50%, and then another 40 or 50% cost increase from going from double pane to triple pane glazing. So that's kind of like getting a sense of what the impact might be on your project budgets. Hopefully, now that it's in the code, costs will start to come down. Next slide, please. So the takeaways is in the city only, we've got new requirements that are weeding out the worst performers. And if you want to get to that extra level of performance required for the high performance glazing, if you want to increase your glazing allowance to above 35%, you're going to have to get a little creative. These are the big takeaways on glazing. And then something I alluded to before, when you're doing your UA calculations, it's going to be more challenging to trade off overperforming glazing against underperforming assemblies. The UA calculations, the component performance path, it allows these trade-offs. This is what I've always relied on my overperforming glazing to make up for my thermal bridges, and that's a lot harder now. So I'm going to take a lot closer look at my thermal bridges when I'm complying with the 2018 code, and we're going to get into that more on the next slide. Let's go to the next one there. Okay, underperforming assemblies. Where are we typically coming up short? So we've got a couple examples on the page here. These are some overall sections of buildings that provide examples of mass transfer slabs that Dwayne was talking about previously. Where do we usually see these? We see these when often we've got a wood frame building on top of a concrete podium where we've got a slab that extends from interior conditioned space to the exterior. Maybe we've got a deck or a courtyard, like on the top right, we've got a courtyard between those two buildings, and there's a mass transfer slab. Can't really insulate that. Same whereas you have on the bottom left there, we've got conditioned space adjacent to a parking garage. That's another condition where we often have these mass transfer slabs. So the code's got some extra allowance in there, but they don't quite meet the code performance values, so we have to make up for those elsewhere. So it's just something to consider up front. Next slide, we've got a window wall slab bypass, something that we all often think about up front, but these slab bypasses, you typically get 2 inches of insulation roughly, maybe 1.5 inches at your window wall slab bypass. So that's R6, R8 insulation. If you've got an IGU spandrel, you can increase the overall effectiveness of that a bit. You're at about R10, maybe R12. In Seattle, this is a mass assembly, you need to be at about R18, so you're coming up short. So this just about gets you there for the state code, but in Seattle with window walls, you may have some ground to make up elsewhere. Concrete curbs are often under insulated. Spandrels can be. It's kind of it's a broader discussion that I think may be addressed in a future code cycle, but we're a little bit too generous with how we calculate spandrel U values currently. It's been allowed. It's standard construction practice to install additional insulation to the interior of our spandrels. But when you consider 3D effects of spandrels, of mullions that go from interior condition space to the exterior, our calculations aren't quite realistic. But that's not in the current code. And then P-tax and concrete balconies, those are items we're going to discuss in upcoming slides.
Okay, as I mentioned before, you can have 35% instead of 30% maximum area, but I just wanted to say that next year will be the 100th anniversary of that photograph hitting the architectural magazine. So we've had like 4 generations of architecture professors oohing and awing over all glass, floor to ceiling, wall to wall. And, you know, eventually it's got to start looking old, right? We have some requirements that we are more strict about with Seattle than some other jurisdictions. We used to require CPD numbers for punched windows for everything. Now we're only asking for them if they're the ones you're proposing are better than code and they're being used for a UA trade-off, just to guard against over-optimistic architects. And then when you get out to the actual construction site a couple of years later, the inspector needs to see on those stickers on the windows that you're actually doing better than at least as good as you promised in your documents. For site built storefront, curtain wall, window wall, etc., we used to require a simulation report, but that was pretty impractical. So we're allowing this thing called an NFRC, a CMA bid report, which is much easier to have put together. And however, the other side of this is that before the first stick of stuff goes up on that curtain wall, you have to have the NFRC label certificate there on site. And this is sometimes pulling teeth from the manufacturer. They like to come out with that thing months after it was already completely built. But you need to have that, and the values need to be at least as good as what was promised in the drawings. So NFRC labeling, that's you, RDH, Jason?
Yeah, just another quick word on that. It's a time-consuming process to attain an NFRC label. You have to do a thermal simulation and then verify it via physical testing. Thermal simulation reports that are third-party, those are accepted by the city at the time of permit. And then for the label certificate, there's cost involved and time to do the physical testing to validate those results. Specify an NFRC label certificate in your specs, get it in the contract, and then mention it early and often. I keep thinking, and a lot of manufacturers have come around to that Cialis actually cares about these requirements and they need to be submitted if you want a permit, but it feels like pulling teeth. So, mention it early and often. And, there's a tip sheet that's snipped onto the page there, 403, just send that to them and say, read it, and this is what you need to provide, and mention it, over and over again. I'm just still surprised that there's still pushback to this, but we want our permit, so you got to meet the requirements that are laid out in that tip sheet 403. Third-party simulation report, a CMA bid report, or a label certificate. And then finally, the CMA bid reports, those are not label certificates, but they, like Jane mentioned, they can be put together quickly, and they're accepted at the time of permit submittal. So those are available for like very common systems that have pre-certified components that they can grab from a database. So those are all good options. Just to be loud about it. Just to make sure.
And I'd say get it on to the construction schedule. When is that CMA bid report going to be submitted? Like, so that it's in time for the permit submittal, and when is the label certificate going to be available, and make sure that's already in their schedule. A word about vestibules. One thing I should say, I put this vestibule in because I think it's like so many, an extremely boring vestibule, and here's a chance to do something really cool, and I see so few people actually do that. But you got to have it anytime it's a building entrance, except for, if you got a little Starbucks or something, can have a separate entrance. You don't, and when I say entrance, it's for where the public and occupants typically go. So if it's just a fire egress door, we have exceptions for little storefronts, for that doorway between the restaurant and the outdoor dining area. You do need to have one for the swing doors next to your revolving doors if you've got revolving doors. And finally, if you've got an air curtain, you can do that instead of the vestibule. So our Passive House representative wasn't able to be with us this morning. I'm going to attempt to rumble through his slides really quickly, just to kind of mention this is sort of another way to look at construction. But you have these levels of requirements for putting together the envelope of a building and the building itself, which ought to stack up there. So you start with quality and health, and then you look for passive things, your glazing orientation and other things, and then you get into and anything that doesn't require mechanical energy, and then you get into active conservation with your heat pumps and so forth, and finally some renewable energy. If you're looking for, just in general, you're thinking about making sure everything is tightly wrapped up in an overcoat of insulation, that you've got your windows optimized for the best use of solar energy at the times of year you want it, balanced ventilation, and that all leads to having mechanical systems that are quite small. If you look at this chart, some people want to get to zero energy by just layering on a whole bunch of solar panels from the get-go, but this chart is meant to illustrate that there's a sweet spot down there where you can get your building energy use requirement down to something really minimized, and you'll see what mostly the Passive House strategies have been able to reduce that heating and water heating load to a small fraction of what it had been in the standard building. And then you can add your solar, and it's a lot smaller solar energy system to meet that amount of energy. And they did a couple of case studies here. You can see that each pair is Western and Eastern Washington and how much energy. And then you can see a code case on the far left for those two. And then, so that's meeting Washington State Energy Code. And then the next one over, you can see if you meet the Passive House standard. And where did all those savings come from? Look at the red part of the bar there. Dramatically shrinks the heating energy of those buildings. And so the two on the sets on the left are for a slab on grade house, and the two on the right are for a crawl space house. Very, very similar amount of reduction. There's if you look at the bottom line on this, you get down to this lower EUI, dramatically lower, getting you to where your renewable energy production is 35 or 40% lower than it would have been with a code minimum. It is code minimum that we have, not a maximum, although many design teams treat it like a maximum. Looking at a high-rise residential, once again, you can see that if you do Seattle code, that's actually pretty good compared with the rest of the country. But going passive house squeezes down those heating and water heating loads really dramatically. Same thing happens out. Actually, even more dramatically happens out in the colder parts of the state, where you can get tremendous gains from buttoning up the building more tightly. There you got Spokane. It's a 27% drop from our state code. He just wanted to mention that Pennsylvania decided to say, okay, if you want to get low-income housing tax credits, you have to build to that passive house standard. They were shocked in 2015 that those buildings only ended up costing 2% more than in construction costs than typical buildings. But even more shocked in 2016 and in 2018 that they did the same thing, but by then the builders were on top of it and it was cheaper. Part of the reason it got cheaper was that their mechanical systems got a lot smaller and simpler. So this high-level energy efficiency is not only great for utility bills in the long run, but if you do everything right, you can get to this amazing sweet spot where it's going to cost you less. So back to our typical part of the talk here. Thermal bridging has been this huge problem. The biggest problem has been these concrete balconies, cantilevered. So yeah, you can use one of those manufactured assemblies that has stainless steel reinforcing bars connecting through a couple of inches of insulation to the deck. Those are expensive, but they got a lot cheaper in the last couple of years. There was, I think there's a North American factory built now. But you can also, and the other one that we had was a fenestration frame, that you have. We have some rules for how you have to align the glass around the frame to make sure that the glass and the insulation line up closely. With a concrete balcony, again, if you want to go ahead and do a conventional penetration through, then you're going to have to do a UA calculation or a C407 calculation and account for that loss through there as though it were an uninsulated mass wall. Concrete balconies, once again, those thermal breaks are great. But there are also other kinds of balconies, and we'll see some more of this in a little bit, that like you see on that bottom drawing, where you just crane something into place and bolt through, that doesn't have that continuous concrete through it. The balconies. Well, RDH, you're on now for balconies.
Okay, yeah, well, just, why are we doing this? So here we've got we did some thermal simulations of these 3 different wall types, effective R value of just the wall itself, ignoring this concrete balcony penetration. So kind of simple calculations of the effective R value of this wall assembly. So if you click again, Dwayne, please. So then we do the simulations. We have an 8-foot, 8-inch high wall. We add in this slab penetration, and what's the overall R value of the actual assembly? It's reduced by 50%-ish. So that's why we're addressing this. Like, this drives us crazy as enclosure consultants. These are huge thermal bridges. They really dramatically affect the enclosure thermal performance. So we're insulating them now in the city. So as we should. Let's go to the next one, please. So, Dwayne mentioned this photo of these 2 top photos, this proprietary system that's a structural thermal break that's cast in. So that's an option. I think still pretty rare, although, you know, folks want balconies. I think they're going to have to take another look at this. You know, there's other ways to go about it though. So these bottom photos, this is from one of Denali projects, so Denali, feel free to chime in, but this is a window wall project. So on the bottom left, we're looking at a slab edge that's got its foil face membrane waterproofing applied to the slab edge. And we've got two steel plates that are projecting out and welded onto embeds. And so that can all be insulated, and then our slab bypass metal panel is installed on the right. After this, a balcony was craned into place and bolted to those. So we still got, you know, we've got some thermal bridging, but this is much improved from a continuous concrete projection through the insulation layer. This can work. There's just some things to consider. If you want to crane in a balcony, where are you going to store the balconies? And what about the construction schedule? How's that going to be affected? So here's a different approach that we took on a project in South Lake Union. There's a lot going on here. I kind of just like to show this to kind of illustrate the complexity and problem working through that you have to go through. But on this project, we couldn't crane in a balcony. That wasn't going to happen. We needed to insulate the slab edge. That was an energy requirement. So what do? We had we developed a system that we could place the interior concrete on the right side of this detail and the exterior concrete balcony on the left side of this detail, which is independently supported at the same time, called simulcast balcony. And we had a stay form at the edge of the interior concrete that we waterproofed with a self-adhered membrane. And then you've got an insulation layer that's shown in blue directly under the window system. And then you've got an insulation layer directly under that. So this is an RFI with a bunch of markups as we're trying to work through the details. We had some problems in construction after the concrete was placed. They did a little damage to the waterproofing. It was a little hard to tie into it later, but we ended up getting there, learned some lessons, and you know, it's a permanently insulated balcony. It's possible. You just have to work through it, get creative, and you know, we can make it happen. Just requires a different approach and some new problem solving. Yeah, let's keep going.
And here, a number of photographs of other kinds of balconies that are not that are bolt-on or somehow only are needing to penetrate the insulating layer with bolts and not with a cantilevered slab. All kinds of examples. The one caveat I should mention is that crane time on some projects is really valuable, and so you might end up having to be craning things into place in the middle of the night. Just want to mention where you got your, well, let's go past these words, and let's just let RDH talk about the alignment of the glazing with the insulation.
Yeah, so City of Seattle has added language to the code that requires alignment of the continuous insulation layer and the thermal break in your window system. There's specific language, there's a section, we're kind of moving right past that, but they need to be aligned, especially with steel frame construction. With wood frame construction, there's a bit of offset required because wood is a decent insulating material. So here we're just illustrating with these examples. The top example here we've got is yellow insulation in the top left, just a basic sketch. It's aligned with our thermal break. And on the right is a thermal simulation of that. And we have a psi value that we've calculated. Psi values are, they're like U factors, except they're not per unit area, they're per unit length. So they measure the thermal transmittance at this interface detail along the length of it. So we've got a low psi value here. This code doesn't require these calculations. We're just illustrating the kind of effects of what Seattle's changes to the code have caused. So very low value there. And on the bottom, we've got a total misalignment. We've got a concrete structure, and the window system is the thermal break, and that's nowhere near it. And we've got a psi value of 0.24. So that's an 1,800% increase. So this wasn't captured in the code previously. There were no requirements around this. We're trying to address it in a prescriptive way that doesn't require, the code is trying to address it in a prescriptive way that doesn't require a thermal simulation expert to run these calculations to show compliance. So let's go to the next one, Dwayne.
Can you define psi value?
Oh yeah, okay. The psi value is it's thermal transmittance per unit length, rather than U factor, which is per unit area. So it's kind of a relative of U factor, but just per unit length. So here we've got a couple examples. The one on the left is beautiful, curtain wall system. Our mineral wool is built but right up to the thermal break in that curtain wall. Works great. The one on the right is we've got on the detail on the right I want to talk about a little bit. The exterior of that detail is on the right side of that shop drawing. And you've got a window system that's plopped directly on concrete that's insulated from the interior. So you've got cold concrete, and we're completely bypassing the thermal control of our window system, which occurs along the plane of the IGU. That's where the thermal break is located, most window systems, and it's completely bypassed. So, we've got cold concrete basically in contact with aluminum, which is a great conductor. This is a real world example on the right. This detail, we have condensation on the interior surface of this window. This is a building in Tacoma. It's humidified. It just goes to show that even in our moderate climate, on the coast here, if we don't have properly insulated window rough openings, we can have condensation issues. These are like the sort of stuff that enclosure consultants are hired to address. So just be careful. I think that the code changes are maybe saving us from ourselves, from some of the sillier decision making that can happen, so that we get those aligned. Yeah, let's keep going, Dwayne. And we're a little short on time. This is just an illustration where we did a calculation. We have a U.35 window now, and then we did a simulation to include the perimeter interface detail. We did a side value calculation, and then we did the math. This is a 6.5 foot square window in our example. If we have this detail all the way around, we don't have continuous exterior insulation, or it's poorly insulated. You've got your window right up against a steel frame. You're actually increasing the effective U value of this window by 33%, from 0.35 to 0.47. So in short, the reason that this language is being added to the code is to address these more egregious examples of thermal bridging at the perimeter of windows. Yeah, so I think I'll leave it there. And this is taking it to the nth degree. This is a passive house project. This is where we over insulate frames. You can really do a really great job of actually improving the thermal performance of windows if you're willing to take a very close look. You've got to be very careful with water shedding. There's a lot of thought that goes into these details. This is what we see on passive house style projects. So there is room for improvement, and you just have to be careful with this sort of thing, because it's atypical construction practice, but we do it when that's what the project's goals are, that passive house level of performance. So let's keep moving, Dwayne.
Okay, well, we promised you a break. We'll give you one, but since Jason and I have been talking a lot, let's make it only 2 minutes. That'll give you time to get up and lean out your door and take a deep gulp of outside air. And then we'll finish off our last 45 minutes of the seminar, okay? So see you in 2.
Thank you for the built-in break. It's always good when you have a couple hours to just get that few minutes to refresh. And again, thank you for everyone that's been commenting. If anyone wants to keep engaging and commenting and asking questions, just use chat.
I'm just seeing if anyone's paying attention. Jeremy's question on radiant cooling with the surface 4 coating. Make sure I understand this. Yes, with the surface 4 coatings, since you're reducing the surface temperature of that window, you may feel a bit colder. And there's some discussion of do you increase the mechanical systems, the heating temperatures, to make up for that radiant temperature when you're near the window, so that you're comfortable. And it's a valid concern. Occupant comfort is determined by the air temperature. and the radiant temperature of the surfaces around it. So if we're decreasing the temperature of a surface, yeah, it might make you feel a little cooler. At the same time, you're reducing heat transfer through the window. So there are savings. It's an interesting topic that we could chat about quite a bit. I didn't mean to leave you hanging there, Jeremy.
All right. We've had our 2 minutes. We're refreshed and re-energized, right? Just want to mention that we had recent legislation at the state level that dealt with blowing agents for various foam insulations, not the foams, but the blowing agents they use to manufacture these. And so we're already into this whole list of various kinds of rigid and spray foam insulation, and the manufacturers were scrambling last year. I think that this year they're getting up to where this is available, but make sure that your that everything is meeting standard now. RDH, Jason.
Yeah, so it was more problematic earlier in the year. I feel like the manufacturers have product now. Just review your submittals to make sure it's the low GWP variant, but that's what folks are selling now locally. Installing anything else is not legal. So yeah, there's plenty of products. You know, Dow Blue Board, it's now DuPont, but it's not blue anymore. It's gray. And Owens Corning, their XPS, it's Foamular. It's what they've always called it now. It's Foamular NGX, and I think it's still pink. But you know, all the spray from BASF, Demilec, DuPont, they've got product available that meets the low GWP requirements. We can keep on going.
Okay, I'm gonna show you one mechanical system slide here, just because this is an exception we put in the code, because now most heating has to be done with heat pumps, but for dwelling units, we put in a 750 watt per room allowance for using electric resistance heat instead of heat pump, or 1,000 watts for a corner room. And so I asked RDH, well, what is it? Is this going to work? Is that enough heat for a room? So Jason.
Yeah, we did a few examples. We just typical multifamily units from projects we worked on, and we did heat capacity calculations. You know, what size heat system's required to keep it warm inside. So here's one example of a bedroom with 10 linear feet of exposed wall area, and we did the heat capacity calculation, and with wood frame construction, about a 400 watt heater is required to heat the space. With steel frame construction and the less performing windows required for unitized glazing, you need about 500 watts. So very feasible for most of these units. This is 40% glazing ratio. If you've got 10, 12, 15 feet of exterior wall, you should be okay. I mean, do the calculations, but it's not really changing typical construction practice was the message we got from the analysis. Let's go to the next one. So it's a 750 watt capacity for typical units, but corner units are allowing up to 1,000 watts, where you can still use the 1 kW and you can still use electric resistance heating. It's a little bit more challenging, so it's really going to depend on the geometry and the amount of windows you have. So we took a case study here. We've got a 24-foot by 18-foot living room with 35% glazing ratio. We're kind of right on the cusp here. So with wood frame construction, you need you're right there, about 1 kW required to heat that space. With steel frame, per our calculations, you need about 1.2 kW, 1,200 watts to heat that space. So maybe a little higher, maybe you need a little more heat than that allowance in the code. But if you really want to avoid heat pumps in your building, consider just upgrading your windows. Decreasing the U value in our example to 0.30, reduce that heat capacity required to 1 kW. It'll be more economic, than installing a heat pump that's going to cost thousands of dollars per unit. Going to a slightly higher performing glazing is likely there's going to be a net cost savings there if you're not interested in installing heat pumps in your building.
Another thing to know is that apartment units require balanced ventilation now from other parts of the code, and so our old routine, which was never really working the way it was supposed to, of having trickle vents in the windows and continuous exhaust through the bathroom, that's not cutting it any longer. And so just since we're talking about window units, we're not ordering the ones with trickle vents any longer. You have to have a mechanical system that delivers air to the space and that recovers heat on the way out. There are different ways to do this. You see a little mini heat recovery ventilator that's available to use for a single apartment. You could be bringing air down and up through vertical shafts or horizontally out to floor-by-floor HRVs. Jason.
Yeah, so I'm going to discuss the architectural considerations briefly on this change. We're really excited about it. It's better indoor air quality. Trickle vents, how well are they delivering air to fresh air to each interior space? Very questionable. So now we're going to deliver an engineered amount of fresh air to each space. It's going to be filtered. It makes sense. So how are these going to be arranged? Mechanical engineers are working through this right now. We've been doing this in Canada for a long time, and we work closely with our Canadian offices, so we've got some more experience there. There's a few ways to go about it. You can do a distributed ventilation, so a HRV in each room that serves just that room. The issue here is decentralized maintenance. Those are typically going to be located in a bulkhead in the room. You're going to have to access that to change filters, repair the equipment, whatever you got to do. So that may not be, that's not attractive for institutional housing, student housing, affordable housing. They want to be able to access that equipment and not have to change out, 80 filters every 6 months. So it makes sense in certain situations. One of the attractive things about this is you're not losing any floor area. That's really important for developers when they're doing those calculations. They're trying to maximize floor area. We've all kind of been through that. So that's one of the advantages of this configuration. Just a lot of penetration. So we got to make sure they're sealed properly. That's something that I obsess about as an enclosure consultant, because when you poke holes in the building, that's a weak point. So to state it mildly, I'll leave it at that. But it's you've got a bunch of holes in your building. They better be designed and built correctly to make sure they're watertight. Let's go to the next one. Okay, here we go. A couple more configurations. Floor by floor HRVs are popular, as are rooftop mounted units that maybe serve a stack of units. You put several up on the roof that serve a certain stack of units. Floor by floor is attractive because you have more centralized maintenance, and the equipment isn't super complicated, and the controls are relatively easy to manage, but typically you're taking up space on every floor to place those units. So that's a big concern. Also, where are you running your ducts? What's your corridor height? Do you have space for everything? Like, take a close look at it, when establishing your slab to slab heights. It's a conversation that really needs to be had very early in design. And with the rooftop units, the ones that serve stacks of units, they're challenging because you need fancy controls to deliver the appropriate amount of fresh air to each unit. There's fire dampers involved. It's just more complicated engineering, and there's an expense associated with that. And you're also taking up rooftop space that you may want to use for solar panels or amenities. So there is no silver bullet. Each of these has trade-offs. If you haven't worked on a project with these before, have discussions with your mechanical engineer early. Start to think about it up front, because it's required for Group R2 housing now. Some spacing considerations. You've got to have your intakes and exhausts. They've got to be 10 foot from lot lines and adjacent buildings. That's in the mechanical code. So simple sketch to illustrate that. Here's a sketch on the next slide, please, Dwayne. So when spacing, your intakes and exhausts, they've got to be 10 feet apart horizontally, and if they're less than that, they've got to be at least 3 feet apart vertically. So it's an architectural problem to solve, And I guess another thing to consider here is what you can do to eliminate exhaust for, especially your units, is it may be very beneficial to you. So for HRVs, they do not take exhaust from, generally speaking, from range hoods for cooking because of the grease, and for dryers because of the length. So maybe you should look at condensing dryers. No penetrations required. They're energy efficient and effective. Often range hood vents are installed. They're required for gas. With electricity, there's some discussion of maybe a recirculating vent that's coupled with an HRV exhaust nearby that can do the trick. That's a subject of debate, but it's something to consider. You're going to be interested in reducing your penetrations just to make this whole exercise of locating where your HRV intakes and exhausts are, your intakes are less complex. On to you, Dwayne.
Okay, PTACs, package terminal air conditioners or package terminal heat pumps. These are the units that you'll find in budget motels around the country that when they turn on and off make these huge roaring noises. Those have terrible air leakage around the perimeter, and they have really bad thermal characteristics. So what we've said, and we picked this up from the New York City Code, that if you want to have these through-the-wall mechanical units in your building, you have to do a UA calc, and you have to calculate the area of those PTACs at 0.5, and that's as opposed to like the 0.052 or 0.056 that other wall assemblies require, and then you have to make up for it with extra insulation somewhere else in your envelope. There are also other things in the mechanical part of the energy code that are discouraging use of these really inefficient and leaky units. There's footnotes in the table is where you'll find where these requirements are living. Wanted to mention renewable energy. We require 1/4 watt per square foot based on the area of all your floors. The last code it was only for your largest 5 floors. And it's different in Seattle than in the state code. The state code still has a table that has a different amount of solar requirement for every different kind of occupancy. And it's not only that, but it's that you have to calculate the actual energy generated by those per year. Yeah, we have to make sure that we have that. It's not. I'll show you. It's not that big of a deal. We also have solar readiness requirement for the rest of the roof that says 40% of the net roof. So the net roof is the gross roof minus any skylights, planted areas, roof decks, mechanical equipment, several other things. And it just requires that you've got periodic sleeves through the roof for carrying your wiring through, and you've got a little bit of extra structural capacity. Last code cycle, this did not apply to multifamily. This code cycle, it does. If you want to know how big 1/4 watt per square foot of solar is, well, 2 stories is 3.5%. 20 stories, it would be 36% of your roof, and that includes the panels themselves and any walking space in between. So, what do you think, Jason, about putting solar on your roof?
I think it's great. There's some things to consider when talking straight just about roofing. I'm an enclosure consultant. People pay me to make sure the roof doesn't leak and to get the right roof on their building, make sure it's installed properly. So what are you going to consider about roofing? So the NRCA, the National Roofing Contractors Association, they take a pretty conservative approach. They don't recommend ballasted systems. They're worried. Ballasted systems are systems that aren't mechanically attached. They're not anchored to the roof. They're held in place by their weight. So they don't recommend those because they're worried that if there's an earthquake, they might shake and damage the roof, or if there's excessively high winds, they might be displaced, and that could damage the roof. So it's not their preference. And they also recommend further that you shouldn't locate seams or anything that might require access for maintenance in an inaccessible part of the, of the roof right below those solar panels. So we've got a ballasted system on the right here. It's from a local project with a single ply roof. And yeah, those points, I'm not going to say they're not valid, but this has become the most common way to install solar panels kind of by far, because it's the least expensive. So it's attractive from that point of view. And it's really difficult to lay out roofing seams so that they're not going to be covered by the ballasted roofing system. We put protection sheets under them to protect the roof from damage should equipment shift or just when it's being installed. So there are some valid concerns, but I don't know that you need to necessarily, dismiss ballasted systems out of hand. They work, they're effective, and it's super common locally. A few other things to consider. This is more related to existing buildings, but what's the lifespan of your roof? Do you have a 20-year roof on your building and the building's 15 years old? You want to put a solar system down. Maybe you replace that roof a few years early. It doesn't make sense, or install in a way that the roof can actually be replaced. Maybe mount it to stanchions or posts so that the roof can be replaced. Without having to remove the solar panels. These are some of the practical considerations. You may also just take a close look. We always recommend these kind of high strength cover boards directly under the roof membrane, so that the roof membrane is not placed on insulation. But especially when you have solar panels, put a quality cover board on top of it. Like Densdeck Prime, Secure-Rock. That's just going to be a solid substrate for your roofing. And finally, take a look at your warranty terms. There's some fine print in some of those that's related to PV system installation. Although I think folks are coming around and just getting on board that this is something that needs to happen, period. And existing buildings, of course, there's solar readiness requirements in the new code, so they have to be engineered to accept future solar panels. But existing buildings, you don't know that up front. How much weight are you adding to the roof? Have your structural engineer take a look at that. Yeah, that's what I've got.
Okay. Somebody took a look at the C406 additional efficiency credits requirement in state code, and they color coded things green for the most economically advantageous, and red for those that were also somewhat economically advantageous for you to pick, since you have to get a number of credits for each building depending on your building type. And so you can see what I've circled there is that for the non-residential types, they saw that doing the better envelope was actually economically feasible, and for all of them, they saw that doing tighter infiltration than code required was paid for itself nicely. I want to just briefly mention energy modeling because we've changed to an entirely different system. The old system is in the trash now. We're using a variation of the ASHRAE Appendix G method, which basically just compares your proposed building to a building that would have been built to the 2004 Appendix G, and it has to be a certain percentage better. So in the state, for an office building, you've got to have no more than 54% as much carbon emissions as the old ASHRAE standard would have allowed you, and in Seattle, with 10% better than that, you have to be no more than 49% as much emissions. We did say in the state code that you cannot use the modeling process to make your building envelope UA any more than 20% worse than the prescriptive code. And in Seattle, you can't make it any more than 10% worse than prescriptive code because basically the reason that people have done energy modeling for code compliance up till now has always been to allow them to make a worse envelope. Regarding existing buildings for additions, you note that you can either have the addition by itself comply with code, or you can consider the entire building, addition plus existing, to comply with the code. And then there's a few more reasons. And if you're over 500 square feet, which is not that big, then you have to start generating those C406 options. For alterations, just some real basic ground rules, things that have been built to code, even if it's 70 years ago, you're fine as long as you're not touching it. You can just leave it the way it is. Anything that's new, if you replace your window units, including frames and glass, those have to meet code. If you replace the roof, there's requirements for that. If you replace your mechanical system, if you're a landmark building, come to us. We'll help you out, making sure that you don't have to do anything that hurts the landmark status of the building. And sometimes there are things that are just impractical. Come talk to us. There are certain things that don't have to meet code, and one of them is called a roof recover, where you're just putting an extra membrane on top of all the existing. But if you're doing a roof replacement, like I think this project that you see in the photograph is, where you're ripping off the old membrane and putting on a new one, yeah, you got to bring your roof insulation up to code. And finally, for most alterations, you don't have to do air leakage testing because, yeah, there'd be some practical peculiarities there. If it's a substantial alteration, which usually is generated by something that we say substantially extends the useful physical or economic life of the building, or if it's been vacant for a couple of years or more, then you have to basically bring the building up close to, but not all the way to current code, not only for energy, but for seismic and life safety as well. We have certain exceptions if you're just doing unreinforced masonry upgrade, if your building has been vacant for a couple of years, but it's relatively new, or if you can demonstrate that it's just not practical, we will not just let you out of complying with the code, but will give you some breaks. You can either go through the whole prescriptive code, follow every rule, or for substantial alteration, you can do everything inside the building to code and have your building envelope be up to 15% worse heat loss, or you can do the whole energy modeling and have it be 10% worse than the basic part. So that's getting towards the end here. We're looking at a carbon neutral future. Buildings, you can see here on the left, a building that was really intended to be temporary 70 years ago. It's still in use. We got to watch these things. So we want to build buildings now that will serve us for generations into the future. And we were able to reserve a little bit of time for RDH to tell us what the future holds.
Not much. I want to leave some time just for questions too. So we'll run through this pretty quickly. I just wanted to also reiterate the limit on substandard building envelopes when you're doing an energy model is a major change to the code, that those can only be 10% worse than the prescriptive code. In the past, people have used energy modeling as a kind of a workaround to get around all these insulation requirements. And there's still a little bit of that. You can be 10% worse than prescriptive code, but not a lot. So you're just gonna, the energy modeling path is no longer a kind of carte blanche to build whatever enclosure you want. And that's a major code change. And I just want to make sure that everyone's aware of that. So, we got a few minutes here, Joanne. We're just going to kind of run through these slides. So we have a few minutes for questions too. This is what we get excited about, super high performance enclosures. This is what we feel like is coming next. So what we have here is a schematic that we worked up of something we informally call curtain wood. We've got CLT panels. You can kind of see a stack joint detail here that mimics a curtain wall stack joint. You've got an anchor that's kind of akin to a traditional curtain wall anchor. We're replacing it with a wood building, plenty of exterior mineral insulation with our furring strips attached to that mineral wool back to the CLT. It's very thermally efficient and effective, and you can keep going down through the slides because there's a bunch, Joanne. I'll just talk over them. And you know, as you go through here, you'll see the various layers that are added to this walls. You've got a weather barrier applied to the walls. We've routed the bottom of the CLT and installed a stack joint receiver. You know, more metal flashing. There's the top of the wall. There's your the so-called chicken head for your kind of curtain wall like configuration there to accommodate vertical slab deflection. You've got your waterproofed walls. We're going to add windows, high performance windows, plenty of exterior mineral insulation. Add our wood strapping for our cladding attachments and dress it up with cladding. This is attractive because wood is, you know, environmentally friendly. With the CLT panels, they can come huge. So here they're applying some gaskets and insulation to our joints. We treat it like curtain wall. We've got to, you know, build these units in off-site and crane them onto site, then we kind of seal them together in the field. It's a similar process to a unitized curtain wall, really. That's the process we're mimicking. CLT panels, here they are getting hung one on top of the other. They can be made really big. We can build these off-site, put them onto the building super quickly. That's okay. There's some debate. Is CLT practical from a fire resistance point of view? Is it too heavy? You know, you can use a steel frame backup wall, you know, with the same concept, and we've done that as well. We see manufacturers, like industry, starting to kind of catch on here. They're coming to market with similar kind of concepts that aren't just our aluminum curtain wall plus glazing. We've got, you know, frame sections with lots of insulation. Our spandrels are properly insulated from the outside. That's what we've got here. You know, yeah, James is going to step over it so we can get through the presentation. You know, I think that there's room for innovation. You know, Dwayne mentioned we're sick of working on these glass towers. It's just a bunch of glazing. I mean, they're cool, they're interesting, and it's good work for us, but we want to be pushing the envelope, and Seattle's the place to do it. So here Dwayne goes kind of following through on this. We're treating our splice joints with a silicone sheet, similar to curtain wall on that photo there. There's room for innovation. You know, there's been a ton of curtain wall construction and on towers in the past 20 years. Let's tweak it to make it more energy efficient. And here we are sealing our vertical panel joints together from the interior. You know, this is just like a curtain wall. We do performance mock-up testing. These are new systems. We put this in the lab, we move it around, test the structural test pressures, water penetration resistance, you know, simulate an earthquake. We want to make sure it works for anything innovative like this. But there's room to both reduce construction time and to make our buildings much more energy efficient. This is another tower. These are conceptual images of, this is designed to be passive house. It's 60 stories tall, and this is a steel frame structure rather than the CLT structure we were showing previously. All our insulation is outside, so we're properly insulating our spandrel panels. The spandrel panels are clad with a, you know, it's a glass spandrel, so it, you know, it looks like the glazing. It's, you know, in a lot of ways comparable to the look of our curtain wall system. We've got a curved metal panel here with this concept. There's room for improvement, in short, over our traditional glass-clad towers, and we're really excited to work with anyone that wants to pursue this kind of thing. This is what we get really excited about, and kind of the next step in improving thermal performance. And one way that the code may address this in next cycles, and I know I'm getting ahead of myself, but so our spandrel calculations, that hopefully they're more realistic in the future. We count our continuous exterior insulation like it's actually continuous. That's permitted, that's conventional practice, that's what everyone's doing. In the future, maybe we'll get a bit more realistic about it and have a more accurate accounting of our of the spandrel sections of our unitized glazing to kind of push us in this direction. And, you know, also addressing some more thermal bridging interfaces. Parapets are a big one that drive me crazy. They often aren't properly accounted for. So hopefully the code over time, we're on the leading edge in Seattle, which is a lot of fun for us consultants. I think we'll continue to tweak around the edges till we, you know, to continue to move the needle in the right direction. There's my
Okay.
soapbox there at the end.
Yeah, there's the soapbox. Armando, we're going to give you a couple minutes to tell about future events, and then we'll ask for some questions.
Sure. No, thank you very much, everybody. Solid presentation, a lot of good content. And thank you for asking those questions that came in the middle. We have a comment from Jeremy, says, inspiring future. I'm going to go through this rather quickly. Please, if we have questions for our panelists, please point them in the chat. We'll be calling them out. But just calling out here, a couple of series going on at Lighting Design Lab, webinars wide. We have our 2019 energy code update for both Washington and Seattle codes. We see the deliveries coming up. Lighting going to be next week, Tuesday from 10 to noon, and followed by HVAC, September 28th from 10 a.m. to noon as well. We also have another commercial heat pump water heating series that we're going to be doing, also co-hosted with Ecotope and DNR International. If you were here with us in February, you saw Colin Gerst present to the code series as well. So we're going to have him back as well. And see the deliveries this Wednesday and Thursday is going to be the why and how for heat pump water heaters from 10 a.m. to 11. So come on and check it out. And then you'll have some engineering deep dives later in October, the 11th and 13th. And I think that is. If you go one more slide, Dwayne, you'll see my contact info and Dwayne's as well if you want any additional questions or comments. Again, the recording of this presentation and slides are going to be on our website, on our resources or education tabs. Both will have the information. Looking to see if anyone has any final questions for our panelists here. Denali, Jason, Dwayne, anything we may want to share?
Do you have anything in the chat there, Armando?
Looking at the chat, not much, not coming in. So I'm thinking people got a good amount of that information coming in. Jeremy, thank you for being our top commenter of the day with both questions and comments. So yeah, barring any questions, I think we are good to go. No, I'm gonna say, yeah, thank you everybody for joining us today. Excited to continue the series. Catch us again and tomorrow and coming next week.
And thanks so much to RDH for putting all this time into it.
Definitely.
Yeah, thanks for having us.
Dwayne, thank you, RDH.
Having us. Let's do it again sometime.
Will do. All right. Thank you.
All right. Take care.
All right. Bye.